All right, let's jump right in. We're going to explore one of the most fundamental forces in the entire universe. It's this invisible power that's running literally everything, from the device you're watching this on right now to the stars in the night sky. Yep, we're talking about electric charge.
You know what I'm talking about, right? That little zap you get when you touch a doorknob, or how a balloon can just stick to a wall after you rub it on your head. It feels like some kind of magic trick, but it's pure, unadulterated physics, and we're going to decode it.
So, what's the secret? Well, it turns out the answer is a property that's just as fundamental to an object as its mass or its color. It's something everything around us has, even if we can't see it. This is electric charge. Okay, so what is electric charge really? I mean, it's a word we throw around all the time, but what does it actually mean? Let's break this core concept down. Think about it like this. Take this pen, for example. It's got properties, right? It's made of plastic, it's black. Well, charge is just another one of its properties. Now, usually things are neutral. They have a perfect balance of positive and negative stuff inside them. So there's no net charge and no shock.
So how do we mess up that perfect balance? How does something get charged? Well, check this out. You start with a totally neutral atom. See? Equal number of positive protons and negative electrons. But then you add a little friction, like rubbing a pipe with a cloth. That rubbing action literally knocks electrons off of the atom. And boom, just like that, you have more protons than electrons, and the whole thing has a net positive charge. It's really that simple.
Okay, so now we've got a charged object. It's not neutral anymore. And this is where things get really interesting, because now it starts to play by a very simple set of rules, the rules of attraction and repulsion.
And the rules couldn't be simpler. Opposites attract, and things that are alike, well, they push each other away. This is exactly why that positively charged pipe can make a totally neutral soda can roll towards it without even touching it. The pipe's positive charge yanks the negative electrons in the can closer, and at the same time, it shoves the positive parts of the can's atoms away. This little separation is enough to create an attraction that pulls the whole can forward. Pretty cool, right?
Okay, this all makes sense. We're just moving electrons around. But that brings up a really interesting question. If it's all about transferring electrons, can you transfer just a piece of one? Like, can you chop an electron in half?
And I love how the source material answers this. It basically asks, am I a fool? The idea is just no way. It's impossible. You can't have half an electron. It's a fundamental particle. You get the whole thing or you get nothing.
And this idea, this all or nothing principle, has a name. It's called the quantization of charge. It means charge comes in these tiny discrete packets. The smallest possible packet is the charge of one single electron. So you can move 1 electron, or 2, or 1 billion, but you can never, ever move 2.5. So we know these charges push and pull on each other. But how hard? How strong is that force, really? And is there a way to predict it? Well, yes, absolutely. You don't need to be a math whiz to get the big idea here, which is called Coulomb's law. It's pretty intuitive. First, more charge equals more force. Simple. But the distance, that's the real game changer. As you pull charges apart, the force between them gets weaker, and it gets weaker fast. Like if you just double the distance between them, the force drops all the way down to 1/4 of what it was. But hang on a second. This whole thing brings up a really deep, kind of weird question. If there's just empty space between two charges, how does the pushing and pulling actually work? This puzzle led to one of the most powerful ideas in all of physics. Seriously, think about it. There's nothing connecting them, no strings attached. So how does a charge way over here have any idea that another charge is way over there so that it knows to push or pull? It's not magic, it's a field. So to solve this puzzle, scientists came up with an amazing concept, the electric field. And the analogy for this is just perfect. Imagine an angry dad sitting in a room. He's not saying anything, he's not doing anything, but his field of influence just fills the entire room with tension. The second you walk in, you feel his presence, even if he's across the room. That's kind of like an electric field. And that right there is the crucial idea. The second charge isn't interacting with the first one directly, across that empty space. No, it's interacting with the field that the first charge has created right at that spot. The field is the middleman, the messenger. And the cool thing is, we can actually draw this invisible field. We use these things called field lines. By convention, the lines always point away from positive charges, and they always point towards negative charges.
And where the lines are all bunched up close together, the field is super strong. Where they're spread out, it's much weaker.
Okay, now that we've got a handle on charges and fields, let's look at a combination of charges that shows up pretty much everywhere in nature and technology. It's a really important one.
It's called an electric dipole, and all it is, really, is a positive charge and an equal but opposite negative charge that are stuck together, separated by just a tiny distance. A perfect real-world example is a molecule like hydrochloric acid. The hydrogen end is a little positive, the chlorine end is a little negative. That's a dipole.
And you might think, okay, so what? Well, this little pair is unbelievably important. Take your microwave oven. The electric field inside it grabs onto the water molecules in your food, which are all tiny little dipoles, and it twists them back and forth, billions of times a second. All that twisting creates friction, and that friction is what heats up your leftovers. It all comes back to this simple little pair of charges.
So think about where we've been. We went from a little static shock on a doorknob all the way to these vast, invisible fields that fill all of space and make our microwaves work. If this one unseen force is responsible for so much, it really makes you wonder, doesn't it? What other unseen forces are out there shaping our reality in ways we're just beginning to understand?